In this video, we're going to be talking about something called a sampling distribution. This is a kind of subtle, kind of difficult idea that's going to be the foundation for what we're going to do for the rest of the semester. So after this topic, the remaining sections, chapters 8, 9, and 11 that we're going to cover, there's really only two ideas in those remaining chapters. And this is going to be the foundation for those two ideas. We're going to be looking at something called a confidence interval in chapter 8, and then something called a hypothesis test in chapters 9 and 11. And this sampling distribution, again, is the underlying foundation that kind of supports both of those topics. So it's going to be a little bit maybe a little bit difficult to understand at the beginning, but I want to make sure we get a good grasp on this because it'll make those topics so much easier to understand if we understand this. Okay, so let's imagine that we are interested in sampling from some population. And maybe it will help if we even do an actual example. Let's say that we are interested in sampling from a population that's, say, normally distributed, although that's not even necessarily important. And let's say we're interested in this case in the heights of specifically women. We want to sample a population of women to determine the average height of a woman. I guess it's kind of redundant, so let's just say average height, period. Okay, hypothetically, if you looked at the entire population of all women, and let's just say we're restricting ourselves to the US, so adult women over the age of 18 in the US. If you looked at that entire population, there would be a true average height. That would be the population mean. So basically, we want mu. This is, again, notation-wise, this is the population mean that we're interested in. But because the population probably has 100 million people in it, there's no way that we're actually going to be able to find this number exactly. So what are we going to do instead? We are going to take a sample. So instead, we'll find x bar, which is a sample mean. And the hopes is that this x bar is a good guess for mu. But I want to point out, there is only one value of mu. This is the true value that we're trying to shoot for. There's lots of different possible values for x bar. Every different sample that I take, I could take a sample of just the women in this class, and we would get an x bar value. I could take a sample of a different group of women in a different one of my classes. I'd get a different x bar value. I could take a random sample calling phone numbers across the country, and I'd get a different value of x bar. Every different group of women that gets sampled will have a different x bar value. The sampling distribution is going to be the distribution of all of those possible x bar values. So, is x bar exactly the same as mu? Almost certainly no. It would be very unlikely for our x bar value, and I'm talking exactly the same. So agrees with to every decimal, 100 decimals long. Is it exactly the same as mu? Almost certainly not. So what is the probability of some of the things? So basically, what I want to talk about is what are some properties of the X bars that we could get, and I want to kind of list out a few ideas. So let's answer these questions, because if we can answer these questions, we'll get a good sense of how sort of the distribution of all the possible X bar values behaves. So do you think X bar is more likely to be greater than mu or less than mu? So, first question. When we take a sample and we find the sample mean, is that sample mean more likely to be greater than the true value of mu or less than the true value of mu? So let's just say hypothetically, the true value of mu is 5 foot 5 inches. And I take a sample in our class. Do you think I'm more likely to get X bar, the sample in our class, to be 5 foot 4, a little bit less than mu, or 5 foot 6, a little bit more than mu? Well, it turns out both are equally likely. We're just as likely to overshoot the true value of mu when we take a sample as we are to undershoot the true value of mu. So they are equally likely. So again, come back to the question up here. Is X bar exactly the same as mu? No. When we take a sample, our hope is that it's close to mu, but it's basically impossible for it to be exactly the same as mu. Because again, when I say exactly, I'm talking about exactly to every single decimal, identical. But we are just as likely to overestimate the true value as we are to underestimate the true value. If our population is nice and normally distributed, right, I'm just as likely to take a sample where our sample mean X bar winds up being a little bit less than the true value of the population of all US women. But I'm just as equally likely to have my sample mean X bar be a little bit bigger than the true value of mu. This tells me X bar is distributed symmetrically. If you're just as likely to overshoot and undershoot, if it looks the same on both sides, it must be symmetric. The second question, is X bar more likely to be close to mu or far from mu? So this one is maybe even a little bit more intuitive. So again, let's say hypothetically, the true value of mu is 5 foot 5, and we take a sample. What seems more likely for our sample, the mean of our sample X bar? So let's just say I take a sample of 100 women. What seems more likely? That the X bar value for that 100 women in my sample is 5 foot 6, so just a little bit more than mu? Or do you think it's more likely that the average height in my sample is 6 foot 1, so further from mu? So again, if mu is equal to 5 foot 5, which seems more likely? X bar being equal to 5 foot 6 or X bar equals 6 foot 1? Both of these, again, the hope is that they're a prediction of this when we take our sample. Which seems more likely to occur? Well, hopefully it's very obvious that this is much more likely than 6 foot 1. We are much more likely to be close to the true value of mu than far from the true value of mu. That's the whole point of taking this sample. When we take our sample and find our X bar value, the presumption is that it's probably pretty close to mu, and we're unlikely to get values that are really, really far from mu. So x bar is more likely close to mu than far. And so what does this tell us? This tells us that x bar has more values near mu than far from mu. So hopefully both of these things kind of make sense. They're hopefully both kind of intuitive. When we take a sample and we get the number that we get, whatever number we get, it's just as likely to be an overshoot of the true value of mu as it is to be an undershoot of the true value of mu. That's what this first bullet point says. And secondly, when we take a sample and we get our value of x bar, that value of x bar is much more likely to be close to mu than it is to be really far from mu. You're not likely, when you take a sample of 100 women, you're probably going to get a number that's close to 5'5". That's much more likely than getting an outcome that's like, 6'1" or something. That is a very unlikely outcome as your average value in your sample. So you're much likely to find values that are close to the true value of mu than you are to find values that are far from the true value of mu. And these two ideas taken together are really important because they tell us a lot about how the different possible values of x bar are going to be distributed. First, it's distributed symmetrically, and it's symmetrically about mu. So mu is in the center, and x bar is just as likely to be to the left of mu as it is to be to the right of mu. So it's symmetric. So we've got a distribution of x bars that are symmetric around mu. And the second one says there's a lot more possible values of x bar that are really close to mu, and there are very few that are out far from mu. And if you keep this in mind, so what I'm saying is let's look at a distribution of all the possible values of x bar. So essentially what I'm saying is x bar is, we can treat it as our random variable. We said, here's the value of mu. I'm just as likely to find a value of x bar right here as I am right here. I'm just as likely to find an undershoot as I am to find an overshoot. These two probabilities should be equally likely. That tells me about the symmetry. The second one says there's a lot more values of x bar that are going to be close to mu, and it's going to be very unlikely to find values of x bar that are way out here far from mu on this side or way out here far from mu on this side. If you combine those two ideas together, what it tells us is the shape of x bar of its distribution is basically something that looks like this. There's a lot more of the possible values of x bar in here close to mu, right? The probability is much higher that x bar is close to mu and much lower that x bar is way out here far from mu. And I'm just as likely to overshoot as I am to undershoot. I'm getting a nice symmetric shape. So it's symmetric about mu with with higher probabilities, let's say it that way, higher probability close to mu. And what is the shape of this? What does this remind you of? This is a bell curve, and it turns out it is a normal distribution. This is what a sampling distribution is. The sampling distribution is the distribution of all the different possible x bars you could get. Any sample you took, you will get a different value of x bar. But most of the samples you take will give x bars that are close to mu, and you're very unlikely to find samples that are way out here far away. So again, if I take a sample of, 10 women, I'm much more likely to find that their x bar is close to 5'5" than I am to find that it's very far from 5'5". How likely am I to find a group of 10 women just chosen at random whose average height is 6'1"? Very unlikely. that doesn't happen by chance. It must mean our random sample wasn't that random and we wound up accidentally sampling the basketball team at UNM or the volleyball team at UNM or something like that. Right? It doesn't happen just by chance that often. There is one last bullet point I want to think about, and it has to do with taking a sample size. We haven't really talked about sample size. Are we more likely to find a value of x bar that's far from mu with a small sample or a large sample? Okay, so let me rephrase this question so it doesn't, hopefully it doesn't confuse you too much. So basically I'm saying, let's take some samples, but let's let one be a tiny sample, maybe a sample of just size 1. Let's just pick one individual. And the other one be a large sample, 10 women, 100 women, whatever the case may be. And let's do it in the context of heights here. What do you think is more likely? Are you more likely to find one woman who's 6'1", or a group of 100 women chosen at random whose average height is 6'1"? Which seems more likely? Well, I've certainly, again, met women who are 6'1". It's not very common, but they absolutely exist. What is much less common is to find a group of 100 women whose average height is 6'1". That is very unlikely to occur by chance. So what this is telling me is we are more likely to find small samples. So small samples will have x bar be more likely to deviate from mu. Large samples will have x bar likely not deviate very much. So be zeroed in on mu. And essentially this is just telling you what hopefully again is kind of intuitive. What's better? If I want to try to take a sample to make a prediction, in this case about women's heights, what's better? Take a sample of 1 woman or take a sample of 100 women? A larger sample is much more likely to be zeroed in on the correct true average height than just picking 1 woman at random. So essentially, the gist behind this is telling us, number one, the deviation in our results is going to depend on sample size. Which is n. And in the way that it will depend on it is that bigger samples are better. Bigger samples yield better results, which hopefully makes sense. That's kind of intuitive. So that is the last important idea about our sampling distribution. So these are the ideas. The x bar values are going to be symmetrically distributed about mu. I'm just as likely to overshoot the true value of mu as I am to undershoot the true value of mu. I'm much more likely to have x bars that are close to mu, that are pretty good predictions for mu, than I am to find x bar values that are way, way off. And those two things together tell me the shape of my sampling distribution, the way that all the different possible x bar values we could find are distributed. They're symmetric, and most of them are close to mu, which tells me we've got a normal distribution. This last point tells me that the way that the deviation, so sort of the spread in how this curve looks, is going to depend on the sample size. And bigger samples will generally yield better results, will yield a result that is more zeroed in on the true value of mu. So let's see how this all bears out in a couple actual examples. Before I do those examples, let's put this together in a definition. So here's my definition for the sampling distribution. Okay. The probability distribution of all the possible values of x bar is called the sampling distribution of x bar. So this is our definition of a sampling distribution. Oops. And it has a few properties, as we just saw. The properties are that basically the sampling distribution of x bar, number one, is a normal distribution. And has a deviation. This is literally going to mean the standard deviation when we eventually look at the standard deviation of this distribution. Has a deviation that decreases as n increases. Right? Basically, in plain English, larger sample size, so n getting larger, means that we're going to zero in on the true value of mu. So as a normal distribution, and I should say normal distribution centered at mu, right? We were equally likely to overshoot and undershoot mu, so it was symmetric about mu, meaning mu is sitting in the center, exactly as I've drawn here. Mu is the number sitting at the center of this distribution. So these are the two main properties that we need to keep in mind for this probability distribution. Okay, so let's look at an example and see kind of how some of this stuff bears out and see if we can get some more insights on some of the behaviors of these sampling distributions. And hopefully, if all of this discussion up here seemed too theoretical, then hopefully this example will make it a little bit more concrete. So let's do an example that we are familiar with. Let's flip a coin. But this time, instead of having the coin have heads and tails, I'm going to assign numbers to the two sides. We're just going to call it side 1 and side 0. So it'll have two possible values. So I want to flip a coin or spin a spinner that only can land on two possible values. So flip a coin with sides 0 and 1, where both of those sides are equally likely to occur. So if I look at a probability distribution for this scenario, what we would have is, here's the values of x and the corresponding values of p of x. And it's very easy. The only values of x are 0 and 1. Those are the two possible outcomes. And what are their corresponding probabilities? Well, if it's a fair coin, which we're assuming it is, it has a 50% chance of landing on the 0 and a 50% chance of landing on the 1, right? Even likelihood of the two outcomes. And if we draw this as a discrete probability distribution here, here's x, here's p of x, then what happens is, again, we've only got these two possible outcomes, and they are equally likely. So we wind up with a very boring looking distribution with two bars that are of the same height, 0.5. So let's take a look at some statistics related to this boring distribution. Let's say we're interested in computing the mean. So if I want the mean of this distribution. And then let's say we also are interested in the standard deviation of this distribution. So for the mean, we have a formula for the mean. It says that mu sub x is equal to the sum of x times p of x. We've done this formula a couple of times, and it's easy, again, when we only have two possible values of x. So in this case, we have the first value of x, which is 0, and we multiply by its associated probability, which is 0.5. And to that, I'm going to add the next value of x, which is 1, times its associated probability, which is also 0.5. And when you do that, 0 times this 0.5 is going to contribute nothing, and 1 times this 0.5 is going to be 0.5. So I'll add 0 plus that 0.5, and the result is 0.5. And it makes some sense when you look at the distribution. The mean is supposed to be the middle of the distribution. Well, we've only got two bars, one at 0, one at 1. What's the halfway point between 0 and 1 for this thing? It's going to be 0.5. The next thing that we'll look at is the standard deviation. And to get the standard deviation, sigma x, there were a couple of different formulas, but one of them involves doing the square root of, we can either do the sum of x squared times p of x, and then have that be the part that we sum, and then subtract the mu sub x squared from that, and then take the square root of this whole thing. So this big ugly formula is just one that we did back in chapter 5. And if we plug into this, again, we can do it by hand. It's not too bad. I'm going to get each value of x squared. So the first one, I'm going to get 0 squared times its associated probability of 0.5. And then to that, I'm going to add 1 squared times its associated probability of 0.5 and add those up. And that will take care of this portion of the formula. Then I need to subtract from this the value of mu sub x squared. So I need to subtract the 0.5 that we got from this mu sub x right here, that's this number, squared. And then I need to take the square root of the big whole mess. And when we do that, again, 0 squared will still be 0, so this term won't contribute anything. 1 squared is still 1, so this is just going to be 0.5. And then 0.5 squared, half of a half, you can think of it, is going to be a fourth. And we could do that on a calculator if we wanted as well. We'd get 0.25 from doing this number squared. So what I've got is the square root of 0.5. That part right here comes from this part. And then I'm subtracting 0.25 from that, which I get from this part right here. And then we take the square root. So it's going to be, in this case, the square root of, what is the difference? 0.5 minus 0.25. We can do it on the calculator real quickly if we want, but it's going to be 0.25. Let me clear that. So 0.5 minus 0.25. Hit enter. And sure enough, we get 0.25. What is the square root of that number? So the square root of a quarter is going to be a half. We'll see that if we do this. So I'll do the square root of this 0.25. Hit enter, and sure enough, I get back to 0.5. So in this case, the mean is a half, and the standard deviation is also a half. And again, both of these kind of make sense. The mean being a half, the mean is supposed to be the center of our distribution. We've only got two things in our distribution, a 0 and a 1, so it should be right halfway in between. The standard deviation says how spread out are the results we get when we actually sample from this distribution. And in this case, this also makes sense. I can't actually get a value of a half when I sample from this. I can only get a 0 or a 1. So if I sampled from this and I got a 0, how far is a 0 from the mean of 0.5? Well, 0 is 0.5 less than this number. What about when I'd sample and get a 1? Well, a 1 is also 0.5 away from the mean. It's 0.5 more than the 0.5. So again, the idea is 0.5 is right in the middle. 0 is 1/2 less than that, so 0.5 less than that. 1 is 0.5 more than that. those two outcomes are equally likely. How far on average are the outcomes from the center? They're half away. The 1 is 1/2 larger, the 0 is 1/2 less than this number here. So both these numbers make sense. Mu sub x being 0.5 in the middle makes sense, and the standard deviation telling me how far are the outcomes on average from that center. Well, this one's 1/2 less, this one's 1/2 more, and so on average, how far are they? 1/2. So there's the numbers. This is what we get from this particular situation. So now what I want to think about is sampling from this distribution. I want to sample, so basically take some samples and look at the possible values of x bar that we get. I want to look at now a sampling distribution from this population. So I want to treat this as though it were the population. So there's only 2 individuals in this population, and I want to sample from it. So let's now sample multiple times. And in this case, let's let our sample size be 3, because we've kind of dealt with 3 coin flip problems before. And this is going to give us our sampling distribution. So when I say sample from this 3 times, I literally mean we're just flipping a coin 3 times, and we're saying it's a coin that has a side of 0 and a side of 1. And I want to look at the results that we get when we sample this thing multiple times. So what is this going to look like? Okay, let's look at all the possible outcomes and then kind of think about how likely each one of these outcomes is to occur. We've already looked at the outcomes. So if we look at the sample space of this, we already did a sample space of this that involved like H's and T's. So it was like heads, 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 tails. Hopefully this looks familiar. We don't have heads and tails anymore. We have 1s and 0s. So I'm going to say, let's redo this same sample space with 1s and 0s. So instead of heads, 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 it's just going to be 1, 1, 1. That's one outcome. The next one is 1, 1, 0. Then 1, 0, 1. Then 1, 0, 0. Then I could get 0, 1, 1. Or 0, 1, 0. 0, 0, 1. Or I could get 0, 0, 0. So here are the 8 outcomes. It's the exact same sample space that we had with H's and T's, but I've converted all the H's to 1s and all the T's to 0s. So these are basically every single possible outcome you could get from flipping that coin, from flipping this coin 3 times. I could get 1, 1, 1, I could get 1, 1, 0, and so on, all the way to the end. I want to use this sample space to now create a sampling distribution of all the different possible values of x bar. So I want to know what the x bar values are and the associated probability of getting that value of x bar. This is a sampling distribution because, again, a sampling distribution is a distribution of all the possible values of x bar. So what do I mean when I say x bar? I mean literally the average outcome in the sample. So for example, this first outcome here, 1, 1, 1. What is the average outcome of this particular result? So I've got 3 1s. What's the average of 3 1s? Well, you can add them together, 1 plus 1 plus 1, and then divide by the total number. And what do you get? You get 1. So one possible value of x bar I could get if I only get 1s. One possible value of x bar is 1. If it lands on 1 all 3 times, then the average result was 1. At the other extreme, what if it lands on 0 all 3 times? Well, in that case, I'd have 0 plus 0 plus 0 over 3. And the average result is hopefully, obviously, also 0. But I'm going to put it at this other end because I'm going to fit a couple more in between. What about this outcome right here? Well, this had 2 1s and 1 0. So if I add 2 1s, 1 plus 1 plus 0, and divide that result by 3, I'll get 2/3. So 2/3 is another possible value of x bar. Again, all I'm doing here, this formula that I'm applying is just the sum of x over n from back in chapter 3. That's all I'm doing. I'm just taking the average of the results that we got, where these are the different values that we got, 1, 1, 1, 1, 1, 0, and so on. So in this case right here, I get 2 1s and 1 0. That results, the average, the x bar value for those three outcomes is 2/3. So 2/3 is another possible value that we get. And if I come all the way over here to this one, we've got a 1 plus 0 plus 0 divided by 3. Well, that's only 1/3. And 1/3 will be the other possible result. So if you think about it, I can either get all three of the outcomes being 1. I could get only 2 of the outcomes being 1. That's this case has 2 1s, this one has 2 1s, and this one right here has 2 1s. There are a few outcomes where we only get 1 1, so I get this one only has a single 1. This one only has a single 1, the rest are zeros, and this one only has a single 1. And all of those outcomes have an average of 1/3. And then there's also one outcome where we get 0 1s. There are no 1s. We only get zeros. The average outcome of that is 0. So these are the only 3 possible values of x bar that can occur. When we flip the coin 3 times, based on this sample space, here are the means of these little lists of numbers. Again, exemplified over here. How likely is each of those to happen? Well, if you remember here, we have 8 total outcomes. Our sample space is of size 8. How many of those outcomes yielded an average, a mean value of 1, so that our x bar was equal to 1? Well, it was just this outcome, so only 1 out of the 8. So what's the probability of that occurring? Only 1 in 8. How many of the outcomes yielded a mean of 2/3, so that our x bar value was 2/3? Well, that was all the outcomes that had 2 1s and 1 0. So here's 2 1s and 1 0, 2 1s and 1 0, 2 1s and 1 0. That's 3 out of the 8 outcomes. So the probability of getting 2/3, there's a 3 in 8 chance of that happening. What about 1/3? That's all the cases where we only had 1 1 and 2 zeros. So here's one of the outcomes with 1 1 and 2 zeros, 1 1 2 zeros, 1 1 2 zeros. That was also 3 out of the 8 total. So that also has a 3 in 8 chance of occurring. And lastly, how many cases where we only got zeros, so the average outcome was 0? That was only this case right here. There was only 1 out of the 8. This is our sampling distribution. And if I draw its histogram, similar to the one that we've got here, I'll get something that looks like this. So now I'm keeping track of all the possible values of x bar and the associated probabilities of those values of x bar. And we had probabilities of a 1 in 8 chance, call this 2 in 8, and 3 in 8. And the outcomes were 0, a 1/3, a 2/3, and a 1. And so let's look at the histogram for this. Well, the 0 had a height of 1/8. The 1/3 has a height of 3/8, as does the 2/3 that also had a height of 3/8. And the 1 has a height of 1/8 again. Let me just move that over to make it a little cleaner. So there we go. This is the histogram corresponding to this probability distribution table right here. Okay. So I want to figure out some statistics related to this. We did the statistics up here of the overall population of just the 1 and the 0. So we found a half and a half. Now I want to find the statistics of this particular distribution. We already did the ones for this. Let's do the ones for this. So same thing. I want to find the mean now of the sampling distribution and then the standard deviation of the sampling distribution. So let's zoom in a little bit and look at this picture. Can we guess what the mean is going to be? Well, again, the mean is just supposed to be the center of the distribution. So where's the middle of this? Well, it looks like it's going to be right here, right? This is dead center, right in the middle. Where is the middle? Well, it's the halfway point between either the 0 and the 1, or you could think of it as the halfway point between the 1/3 and the 2/3. The point is, the mean right here I think it's going to be 0.5. I think it's going to be a half. The center of this distribution should still be the same halfway point as the original. So let's see if that bears out when we actually do the formula. So when I talk about the mean, the symbol I'm going to use in this case, when I talk about the mean of a sampling distribution, up here, I did mu sub x for the mean of a generic probability distribution with a random variable x. But now our random variable isn't x, it's x bar. So I'm going to change my notation similarly. It's going to be mu sub x bar. This is the mean of our sampling distribution. And in this case, it's the same formula, but with x bars instead. So it's just x bar times p of x bar. Same approach. Take the value of the random variable, multiply it by its probability, and add them up. So in this case, we can do that. Just do it down here. The first value of x bar that we had was 0, and it had a probability of 1/8. So I've got a 0 times a 1/8. The next value of x bar was a third, and that had a probability of 3/8 of occurring. The next value was 2/3. That had a probability also of 3/8. And then the last one was 1, and that had a probability of, again, 1/8. And so we can add these up. This first one is just going to be 0. 0 times anything is still 0. This one can get cleaned up a bit. I can cancel the 3's when we multiply across, and it's just going to be a 1/8. So I'm going to have 1/8. I can do the same thing here, cancel those. I'm going to leave it as 2/8 because we're going to add them. We need a common denominator, so let's leave the common denominator of 8. This one is 2/8. And then the result of this one is another 1/8. And when you add those up, when you add fractions, again, you add the numerators, but you leave the denominator the same. So I'm going to get 1 plus 2 plus 1. That adds up to 4. The denominator stays the same, 8, which is indeed 1/2, or as a decimal, 0.5. So as we anticipated, this value right here, the mu sub x bar, does indeed equal 0.5. And it's right halfway in the middle. So looking at the sampling distribution and comparing it to the population, which is what this was. So this, maybe I'll clean this up a little bit. Let me get these out of the way. Delete that. Up here, I said this one was the population. This one here is the sampling distribution. Let's compare their two means. What was the mean of the population? It was 0.5. What is the mean of the sampling distribution? It is also 0.5. So they agree. I get the same value, and that is going to happen 100% of the time. And the reason is, going back up to the picture that we have here, the sampling distribution is just this big smooth curve. What is the average of this big smooth curve of all the different possible x bar values? It's centered right here at mu, which is, again, the population mean. So the population mean and the average value of all these different x bars will also be the center. They'll be the same center. The sampling distribution is centered around the population mean. The sampling distribution is centered around the same thing as the population mean. So in this case, that's 0.5. So I'll write that down in a minute, but basically this is always going to happen. The average of the sampling distribution, this mu sub x bar, it's always going to match the original mu from the population itself. What about the standard deviations? So let me zoom in here a little bit so that we can write a little more cleanly. See if I can get it all on the page at once. There we go. Good enough. So what about the standard deviation? We have a formula again for the standard deviation. It's going to be the same as the old formula, but with an x bar. And it looks like the square root of the big mess that involves the sum of the x bar values squared times p of x bar. And then I'm going to subtract off mu sub x bar, which we just found, squared, and then take the square root of that whole mess. We can do this either by hand, which isn't going to be too big of a deal. I guess we'll just do it by hand here, but you can also just go back and do this in Excel or on the graphing calculator, the way that we did standard deviations of these distributions. It's not going to be too hard of a thing to figure out, but let's just take a look real quick. So plugging into this formula, what are we going to get? So now what I need to do is, first of all, let me keep my big square root sitting here. But I need to take every value of x bar and square it. So that's all of these values over here. And then I need to multiply each of them by the appropriate probability. So I'm going to have 0 squared times its associated probability, which was an eighth. To that, I'm going to need to take the next one, which is a third, 1/3 squared times its probability, which was 3/8. Then I'm going to have to do 2/3 squared times its probability of 3/8, plus the 1 squared times its probability of 1/8. And once I've done adding them all up, so far we've done this part of the formula. We've added up each value squared times its associated probability. After that, I need to subtract off the mean mu sub x bar that we just found squared. So I need to subtract off this 0.5 squared. So minus a 1/2 squared. And then take the square root of that big, ugly result. So again, please do not do this by hand. This is just to demonstrate the idea. You're never going to have to do this in practice on your own. I just want to demonstrate an idea, and we'll be able to use a formula going forward. Okay, this term 0 squared is still going to be 0, so this term's not going to contribute anything. This one will be, I'll have a 9th when I square a third. A third times a third is 1/9. So I'll have a 1/9 times 3/8. The next one will be 4/9 times 3/8. I'm adding those. And the last one will be plus 1/8. And then I'm going to subtract off a 1/2 squared. When I square a 1/2, I'll get a 4th. Put that all in a big ugly square root. We can try to simplify these a little bit if you want. It's not a big deal. I can factor out a 3 here and simplify that to just having a 3 left in the denominator. This isn't all super important. Let's just plug this into the calculator. So I want to take the square root of the result that we've got here. So let's do all of these. I'm going to do 1 divided by, let me just do the version, let me cancel stuff just to make it easier to read. We'll just do the unsimplified version because it won't make a difference. Let's type these in. So I want a 1/9 times 3/8. To that I'm going to add 4/9 times 3/8. To that I'm going to add 1/8. And then I'm going to subtract 1/4. And that's going to give me a big ugly number on the inside of this that then I'm square rooting. I'm going to just hit enter and see what we get. And boom, there's this big ugly answer. This whole ugly mess simplifies to, let me try to get this squared out here so we can see them both at the same time. So it's 0.28867513446. It is definitely not the same as the standard deviation of the original population, right? Here's the standard deviation of the original population. It was 0.5. What's the standard deviation of ours? It's 0.28867513446. So how on earth are these two numbers related? Well, here's something I want you to think about. We said back here, the properties of a sampling distribution, the last point we made, are we more likely to find an x bar value that's far from mu with a small sample or a large sample? What this led to was the idea that we're going to get a deviation that decreases as n increases. The standard deviation of our sampling distribution should depend on n. We should zero in on the true value of mu, so the result should be less spread out, the larger that n gets. So keep in mind, this answer must depend on n. And how so? Well, let's just see what happens if I take the following result. I'm going to take 0.5, which was the standard deviation of the population. So I'm taking this value up. Come on, there we go. Taking this value, the standard deviation of the original population, and I'm going to divide it by the square root of 3. So let's do that over here on the calculator. I'm going to take 0.5 and divide it by the square root of 3 and hit enter. And what do we get? We get the exact same number that we just got here for the standard deviation. Notice that this number on top is just the old sigma x. It is the, let's just write it in words to make it easier. This is the standard deviation of the population. And what do we have on the bottom? This is simply the square root of n, our sample size. In this case, our sample was of size 3. We flipped the coin 3 times. And so that is going to be the dependence. All of this is just to demonstrate the following. We have, just maximize this again so it's easier to read. What we have out of this is a new rule for statistics of a sampling distribution. So the point in going through this example was to highlight a couple of things. We're going to have the mean, and we're going to have the standard deviation. These are the ones that we care about. The mean we write as mu sub x bar, and it turns out it is the same as mu, or that is just the population mean. So the mean of a sampling distribution matches the mean of the population that we're sampling from. And that kind of makes sense if you think about what we're saying here. I know this is a lot of jargon, but think about this in plain English. I'm saying that the average result, when I take a sample and I find x bar, I would expect it to be close to the population that I'm sampling from, to the mean of that population. That's the whole point of taking a sample. When we take a sample, we want our outcome, our x bar value, to be a guess for the true value of mu, the population mean. Our sample mean is always a guess for the population mean. And this is telling us that on average, if you look at all the different x bars you could get, indeed, they approximate the true population mean. The standard deviation, which we will denote as sigma again with an x bar, it turns out that it is also related to the standard deviation of the original population. So here's the population standard deviation, but it's not the same thing. It's that standard deviation divided by the square root of n. This term is often referred to as what's called the standard error. And it doesn't really make a lot of sense in this context why we call this the standard error, but it'll make more sense in some of the upcoming sections. But let me give you just one quick way of kind of thinking about what I'm saying. What it's saying is if we are trying to approximate a value, so let me give you a distribution here, and here's the true value of mu. And this is a distribution of all the different x bar values. What we're going to get is our sampling distributions are going to look like this. They're going to start off in this shape. And maybe this one occurs for, this is what it looks like with a sample size of, I don't know, maybe size 10, something like that. But as we take a larger and larger sample, we should expect our sampling distribution to get more and more zeroed in So maybe this one is at n equals 100. And notice both of these have the same, or at least they're supposed to have the same peak, but which one has results that are more spread out? Well, a lower sample size has results that are more spread out. I'm more likely to get x bar values over here that are far from mu. So out in the tails of this distribution, which is more likely to have values over here? The case where n equals 10, so this curve, or the case where n equals 100, which is the curve below it? Well, this one is much more likely. This is the same idea. Am I more likely to find one woman who's 6'1", or a randomly sampled group of 10 women or 100 women whose average height is 6'1"? We're much more likely to find these outlier values when the sample size is small. And as the sample size increases even more, we will continue to get results that are less and less spread out and that are more and more zeroed in. So maybe this one is n equals 1,000. Right? We aren't necessarily for sure going to get an x bar value that's right on top of mu, but we're getting x bar values that are closer to mu. All of this is just summarizing that a larger sample yields better results. And what do I mean by better? I mean more zeroed in on the correct value, more zeroed in on mu results. And that's exactly what this standard deviation, this standard error is giving us. So if you think about it, if you take a sample and we're thinking of this standard deviation as basically telling us how much error can we expect in our sample? How far off can we expect our x bar to be from mu? You can think of that as error, right? When we take our sample and we find x bar, we already said it's probably not exactly identically equal to mu, but hopefully it's close. How close? Well, the standard error tells me how close I can expect it to be. The larger the sample size, the smaller this standard deviation is going to get. The smaller the standard error is going to get, and the more zeroed in on the correct answer I can expect to be. So this is sort of the intuitive picture behind what this formula is showing. We're zeroing in on the correct answer. Okay, so all of this in mind, I want to point out a couple nice features and a couple other important ideas and points. So important ideas. Not that the ones that we just talked about aren't also important. These are just important ideas that I haven't mentioned yet. Point number one. Even if the initial population isn't normal, so if the population doesn't follow a normal distribution, the sampling distribution still will be normal, as long as you take a large enough sample. Okay, so basically it's saying, even if the initial population isn't normal, if it does not follow a bell curve, if it doesn't, the population we're sampling from doesn't follow a bell curve, the sampling distribution is still going to be a normal distribution, as long as we take a large enough sample. How big is large enough? Our cutoff is going to be that sample size needs to be greater than 30. So 30 is going to be our size of our large sample. We can go back and look again at the pictures that we just did right here, and it kind of demonstrates this idea. In this case, the original population is totally flat. It's definitely not a normal distribution. This is what we called a uniform distribution. It's flat. And even after we'd only taken a sample of size 3, what was the shape starting to look like? Well, we have more stuff in the middle, less stuff out at the edges. It's symmetric. It's looking like a very pixelated, blocky version of a normal distribution. And as we took more and more samples, so if instead of having n be equal to 3, if I let n be equal to 30, we would eventually have a point now where we'd have enough bars that this would look like almost a smooth result, and it would be close enough to a normal distribution. So even if the initial population isn't normal, if it's flat or if it's skewed in some way, the sampling distribution still is going to be normal as long as we take a large enough sample. And our cutoff for what we'll consider large enough is 30. Again, I say it will be normal. I should really say it will be approximately normal. It'll be close enough that we won't care, that we'll just treat it like it is normal. This essentially is the idea behind what's called the central limit theorem. And I guess I should just write this out because this is the big idea for this section, the biggest big idea. And it's going to be just a more elegantly stated version of what I just wrote. So if we, let me zoom in and so I can write this a little more clearly. If we let x bar be the mean of a large sample, and again by large, I simply mean n greater than 30 sample from a population, so we're sampling from a population with a mean of mu and standard deviation of sigma. Then it turns out x bar follows an approximately normal distribution with a mean of mu x bar equals mu and standard deviation of sigma x bar equals the original sigma over the square root of n. So this summarizes basically all of our findings from this section. The central limit theorem tells us that the x bar is going to follow a sampling distribution. That sampling distribution is approximately normal, where the mean of that sampling distribution matches the mean of the population, and the standard deviation of that sampling distribution is the same as the standard deviation of the original population divided by the square root of n. Depends on the square root of n. So real quickly, I want to show you maybe one example where we can put this to use. And the calculations can all be done in the exact same way that we did them in the previous section when we were just dealing with a regular normal distribution as opposed to a sampling distribution. So let's look at this. Let's say that the mean age of C&M students is, I don't know, let's say it's 27, geez, I really can't write here. It's 27.4 years old with a standard deviation of, let's say, 9.2 years. What is the probability in fact, let's do it this way. Let me rephrase this. Let's say a sample of, I don't know, 60 students is drawn. What is the probability that the sample mean is greater than 30. Okay, so the idea is we have a big group of students at CNM, and I'm claiming the average age is 27.4. That's a made-up number. I have no idea what the average age is. And the standard deviation is 9.2, also made up. And we're taking a big sample. We want to know what's the probability that the sample mean, so the mean of these 60 students that we drew, is greater than 30. So obviously, we expect, if we take a sample, we would expect that the sample mean should be pretty close to this number. We would expect to be close to 27.4. And the larger we make that sample, the more zeroed in on this 27.4 we would expect to be. So in this particular case, when we took a sample of size 60, the question is how likely are we to be this far from 27.4, right? This is, more than a little bit over 2.5 years older. Is that an unlikely thing? Is that an unlikely thing to see? Or is it likely? Or exactly how likely is it? So this is exactly like the problems that we had before, where I'm going to start with a picture. And the idea is in this picture, this is the distribution of all the possible x bar values. We know that the mean is 27.4. And the answer that or the cutoff that we're interested in is 30, which is definitely a number to the right, somewhere over here. But the question is, where does it fall? How big is one standard deviation on this curve? Well, the tricky thing is if we eyeball one standard deviation, which I usually draw to be about here-ish, that should be not 9.2 years more than this, because the standard deviation here isn't just the same as the standard deviation of the population. Instead, it's the standard deviation of the population divided by the square root of the sample size. So this is our same as our mu sub x bar value, but this needs to be our sigma x bar value. And what is sigma x bar? Well, we need to remember sigma x bar is not just 9.2, but it's 9.2 divided by the square root of, in this case, 60. Right? It's always going to be the original sigma divided by the square root of n. So that's where I'm getting these numbers. So what do I get when I do that? Let me plug that into the calculator here. So what did we just say? It's 9.2. I guess I'll do it with the mouse here. 9.2 divided by the square root of 60. And I hit enter, and we get about 1.1877. So I'm going to round that up to 1.188. So this number is about 1.188. That is the distance, 1.188, right here. And that means that this age right here, one standard deviation out, is only a year and change more than this. So it's going to be what, like 28.588? 28.588? All I would need to do is add this number to figure out how far over we've gone. So we're still not to 30. And then I could add another one of these, and I'd be up to 29.7-ish, something like that. And we still wouldn't be to 30. And so we need to figure out exactly where the 30 falls. It looks like the 30 is going to wind up falling pretty far over here. But to figure out exactly where it is, and then we're going to be interested in finding the probability that the age is more than that, so to the right of that. This is the region I'm interested in. We just don't know exactly where 30 falls. I know it's to the right of here. I just don't know how far to the right. So this is the probability that our x bar is greater than 30. It's that area. To figure that out, so here's the x bar equals 30 mark. What is the corresponding z-score right there? And so that's what we need. I will find this z-score. So if we want the z-score there, I will do 30 minus the average of 27.4 and then divide by the standard deviation, which is the 1.188. So for this section, just keep in mind, I guess I should maybe write out the full formula before I do this. It's x bar, sorry, yes, it's the x bar value of interest minus mu divided by sigma over the square root of n. And for us, the x bar value we were interested in was 30. We were subtracting off the average of 27.4 and then dividing by sigma over the square root of n, which we just said was 1.188. And if we plug that into the calculator, which again, let's do that way. So I'm going to do 30. Let's do it all in parentheses, actually. So 30 minus 27.4. I'm dividing that by, let me do this also in parentheses, 9.2 divided by the square root of 60. And then click over and close my parentheses. So we already found this number. I could have just typed in the 1.188, but this way it'll use an unrounded version of the number, which is even better. It'll use all the decimals. So let me hit enter. And sure enough, this is giving me a z-score of about 2. If I had to round that to 2 decimals, I'd say that's 2.19. So this is a z-score of 2.19. And so how do we find that probability? We can do it on the calculator the way that we did before. We could use the tables. Let me add a table here real quick. Just had them earlier. Just got to remember where I put them. It's these, the appendix tables, and it is only those 2 pages. Okay, so here are those pages, very inconveniently placed. In fact, I don't need this one. Let me delete that one because that's smaller values. I just need this one. So I want the area to the right of 2.19. So here is 2.19. And there's the number, but again, this is the number to the left. We want the area to the right. So 0.9857. So what I'm saying is that the probability that x is greater than 30, sorry, the x bar is greater than 30, will be the same as the probability that the z-score is greater than 2.19, which using the rule of complements is going to be 1 less than the probability that z is less than or equal to 2.19. And these are the only types of problems that the table can be used for. It can only do less than problems. This is the number we just looked up, the probability that z is less than 2.19, so basically the area to the left of 2.19, and it's 0.9857. And so I can do 1 minus that number, 1 minus 0.9857, and get my approximate result. My guess is 0.0143. That is the probability that the average age in my sample would be greater than 30. It's not very likely to happen, right? 1.5%-ish. So the only difference between the problems in this section and the problems that were in section 7.1 and 7.2 is that we need to modify the denominator of our z-score to be the standard error. We aren't using sigma anymore. We're using sigma over the square root of n. So anywhere sigma showed up, we're now using sigma over the square root of n. I could do this on the calculator. If we have a graphing calculator, just do that really quickly. And similarly, you could do this in Excel. So I'd go to my list of distributions, go down to normal CDF. In this case, my lower bound, I was going to make 30. My upper bound is basically infinity, so 1, that little double E symbol, 99. My mean, my average age was 27.4, so 27.4. And the standard deviation now, this is where I need to keep in mind. The standard deviation is not 9.2. It's 9.2 divided by the square root of 60. Right? I need to use the standard error. I need to use this number, which is about 1.18. And then I'll hit paste and have it compute the answer for me. And very similar to the number we got here, I got 0.01429, which again will round to 0.0143. Same number we got here. So that's how we can do that on the calculator. Similarly, just real quickly, let's see if we can do this on in Excel. And again, remember in Excel, we're going to have to use the rule of complements. Excel kind of works the same way using the table does. So I will do my equal symbol. We're doing a normal distribution, so norm dist of, it'll ask for the x value of interest, which was 30, the mean, which was 27.4. The standard deviation, this is that ugly number, the 9.2, will it let me type it in like this, square root of 60? Let's see if it lets me type that in or if I have to compute that separately before I plug it in. And then true, because I do want it always to be cumulative. Let's see if it'll let me do that. And sure enough, it lets me do that, but all it gives me is the 0.9857, which matches the number here. If I want the actual answer, I have to use the rule of complements. So I have to do 1 minus this result to get the probability that I actually wanted, which is 0.14296. So again, hopefully you can see this. If not, let me see if I can, no, that won't make it any bigger. Neither will this, for some reason it's just not going. But we can find the answer again using the normal distribution function in Excel. And we just need to keep in mind that when it asks for us to do the standard deviation here, we need to use the standard deviation that is the standard error that involves dividing sigma by the square root of n. So that is the one thing you need to keep in mind. But otherwise, that is it. These problems, homework-wise, are very similar to the ones from the earlier sections, with only that minor change in terms of how we treat sigma. It's now sigma over the square root of n for the standard deviation. This sentence right here, the central limit theorem, needs to make sense to you. And in addition, it will really be helpful if you understand kind of these big picture ideas from back here at the beginning, that all of these make sense. We are getting a normal distribution out of this thing. The sampling distribution is a normal distribution. It should be centered around the true value of mu, right? Some of our x bars will be guesses that are a little bit high from the true value of mu. Some will be a little bit low compared to the true value of mu, but most of the x bar values should be pretty close to the true value of mu. And the larger the sample I take, the more zeroed in on the true value of mu I should expect my x bar values to be. So we should get a result that, again, as n gets larger, as we take a larger sample, I should expect my bell curve to really zero in on the true value of mu. If those ideas make sense intuitively, it's going to help a lot in the upcoming chapters.